All right, welcome to the Rust and Eclipse talk, even though probably people are still pouring in, but I've got a lot to show, so I'll start right now. So my name is Max Bureck, I'm from Fraunhofer FOKUS in Berlin, and today I will talk mostly about Rust, but also about the IDE story and Eclipse Corrosion, which is the Eclipse IDE for Rust. And I'll start with an introduction. So Rust considers itself a systems programming language. This means that it is a right fit for programs where you have tight memory management constraints, you want high runtime performance, and maybe low energy consumption. It's considered an alternative to C and C++ or a complement to C and C++. And for example, it's used inside of Mozilla Firefox right now, and also Dropbox is now a heavy user of Rust. So it is compiled to native code. It is a front end to the LLVM compiler toolchain, which you may know from the Clang C compiler, C, C++, so C family compiler. And its motto is safe, fast, productive, where safe is runtime speed, maybe not at the moment compile speeds, and productive is compared to other systems programming languages, and we will see later why. It's an interesting language because it has influences from like very low-level languages like C++, but also like functional languages like Haskell, the ML family like OCaml, and a research language called Cyclone. Not Eclipse Cyclone, that's different, also a cool project, check it out, but I mean here the programming language. All right, so when you get started with Rust, before I forgot, the first question I want to ask was, like, do you consider yourself a C++ programmer? Please raise your hands if you consider yourself a C++ programmer. Okay, no one in the room. Java programmers. All right, many Java programmers. Oh, I see one C programmer here. So at least a few references will be in order. Okay, so the first thing that you would do when using Rust is installing rustup. Rustup is a version or install manager for Rust, which you can use, for example, to keep your Rust stable toolchain up to date, because there's a release every 6 weeks, not month, weeks. Which means the programming language is on a train model and evolving pretty fast, even though they had since 2015 they were backward compatible. And there will be a new version, edition, coming out like later this year, but it will be backward compatible to previous versions, so there won't be a break like in Python 2.3. And what you will gain when installing a Rust version is a build tool, which comes with the Rust compiler, and usually you would invoke the build tool, cargo, since many of you are Java programmers, a parallel would be Maven, and it can also download dependencies from crates.io, which is the package registry, which is similar to Maven Central. Right, there are several other tools that you can install via rustup or are by default installed via rustup, which I don't have the time to go into. You can later look in the slides. There are also more slides because I have information for hours to talk. And in this talk, I won't cover the complete Rust because it's a language with many features and concepts. So in the end of the talk, I have further reading material. If you're interested, you can learn more about Rust in the sources that I will present in the end. So, buckle up. The first example is already unnecessarily complicated, just to show you some examples on real-world usage, and maybe let's get the laser pointer away from the cat. All right, so here's my unnecessarily complicated hello world example. The first thing that we do is we define a main method. Note that there are no arguments passed to the main method. And what we do first is a module import. In Rust, you can either create a binary or a crate. A crate is basically a library that you can upload to crates.io, to the package registry. But here we use a module that is coming with the standard library, okay? So we use std-env for environment. And what we do now is we declare a variable, a typed variable declaration here of the let keyword, variable name, :type. And the option type is similar to the optional type you now have in Java, but also there's an option type, I think, in standard C++ now. And we assign it a value here. First we call args, which will return an iterator over the arguments to the program. So instead of passing the arguments as an array or something here, we get an iterator. The iterator is similar to a Java iterator, but it has like combinator methods on it, like Java streams, for example. So what we do is we skip the first parameter, because the first parameter is the location of the program that is called. And then we call next, and next returns an option. And if there are elements still in the iterator, you will get a filled option or an empty option if there's no further elements in the iterator, right? So when the program is called with one parameter, then we get the parameter in the option here that is then stored in first arg. All right, talked about the iterator. And now we declare another variable, and you may ask, so this is a reference type, you may ask, we have string here and stir here. Are there two string types? One is an owned and one is a slice type. This is like usual in Rust. You can have like owned memory, and you can have like a view or a window into a string. So this and stir could be, for example, a subset of a string. And there are even more string types, but I don't talk about them because usually you wouldn't get in contact with them. All right, so what we do next is we declare another variable, but the type is inferred. We don't explicitly specify the type with :type. We assign a value, and it is inferred what type this value is. All right, so we match against this first arg, and we destructure the option here. There are two possibilities. It could be a sum of a string or none. So in the case of sum, we bind by a reference the name. So a reference to a string is an and-stir, right? So we return the and-stir of the name out of the first arg variable. Or in case of none, we return the default world here. So world is also an and-stir, so the type of this variable will be and-stir. And going further, we print this variable here, and you might ask, what is the bang here? The bang is a macro invocation. So macros are an enhancement over the macros that you may know from C and C++. They're hygienic. I don't know all the details about hygiene of macros, but what I know is it cannot interfere with the variables declared outside of this macro. And why is println a macro? Because it can check at compile time. There are placeholders here. They're replaced with values that are passed to the macro, and it will ensure at compile time that there are the exact number of spaceholders here as parameters passed in. So it won't compile if this doesn't match. And what does it print out? Well, if you pass a parameter to the main method, it will say hello parameter. If you don't pass an argument to the method, to the program, sorry, it will say hello world. All right, so whenever I have code examples, in the bottom there is a link to like an online playground where you can play around with Rust with the examples without even installing anything on your computer. So you can compile and run the examples. All right, so I will not talk about like primitive types because they're pretty similar to other languages. So I won't talk about ints and floats and bools and arrays and slices into arrays and tuples. I will just talk about the user-defined data types. One of them are the enums, and the enums are basically tagged unions. So they're like C-union types, but in a safer way, because there is a tag always associated with it, or, well, in some cases the compiler can compile away the tag, but anyway. And they have different variants, and a value of that enum type always is one variant of that. Okay, what does it mean? Let's see two very basic enums that are defined in the standard library that you would use all the time, all right? So here we have the option type, which is, as we have already seen, either none or some of t. So these are generics. Yeah, what I forgot to say, Rust does not have null pointers and does not have uninitialized memory. Memory has always to be initialized. If you want something like a null reference or a uninitialized memory, you would have to use an option type for that. The result type is used as function returns usually, because Rust doesn't really have exceptions. There's a panic which does similar things like exceptions, but this is really exceptional. The panics results are returned from functions and can either be a value okay, so that's the expected outcome, or if an error occurs, you would return the error variant with an error type. Okay, so it's very different from Java enums, right? Because these are not like static fields, so to say, but they can hold values. So example usage, we declare a variable OS, and we assign a option sum value to it. Actually, the option : is usually not needed because Rust will import that for you automatically, so you always can write sum. Okay. Structs. Structs are groups of named values, very similar to what you have in classes with class members. All right. So how would you use this struct here? This example is a caterpillar. Fun fact, when I did all the examples, I used the caterpillar, and then later on found out that I sometimes have problems pronouncing caterpillar, so I'm sorry if I mispronounce caterpillar. So it has two fields, a name field, an own string, and hunger, which is a U8, which is an unsigned 8-bit integer, so basically a byte. Okay, so let's initialize a variable with a value of caterpillar. So you write the type, curly braces, assign the fields. As I said, you have to assign the fields because there's no uninitialized memory in Rust. And end with a semicolon for the assignment here, the variable binding. All right, so let's go to memory management because that's the most interesting part of Rust. Rust ensures safe manual memory management, which is checked at compile time. So there is no garbage collector to ensure memory safety, and it does not fundamentally rely on reference counting. There are reference counting types in Rust, but basically most of the time the so-called borrow checker will help you write safe memory management. So the memory management is built around the concepts of ownership and borrowing. So you either own a piece of memory or you borrow the piece of memory. And borrow is basically taking a reference to that owned memory. Ownership can be transferred, and if you transfer ownership, then the original piece of memory that you had cannot be used anymore. We will see an example soon. All right, let's first talk about immutable borrowing. All right, so we have a caterpillar again. We assign it to a mutably owned variable. And now let's take a reference. Let's borrow this owned piece of memory. So we use the ampersand. We take a reference to the caterpillar. If you're coming from a C background, this syntax will not surprise you. And you have now a variable of the type and caterpillar. Note this is not mutable, so we can read the memory now, but we cannot write it. So you would, when you want to access fields of the referenced caterpillar, you have to dereference them and then use the dot notation to get to a field. But actually, the star here to dereference the reference is most of the time not needed, because Rust can infer that you need a dereference there. So it will auto deref until it can access a member that you want to access. We'll see an example in the next example. So we can now read the field hunger, but we cannot write it because we only have an immutable reference. So let's take a mutable reference. Let's mutably borrow. So we say and mute on piece of memory, and now we get an and mute caterpillar, so a mutable reference to the memory. And see that we don't dereference here, we just say dot hunger. So the dereference will be automatically inserted by the compiler. And since we have a mutable reference, we also can change fields on this piece of memory. All right. So now let's transfer ownership. We have again the owned caterpillar, and we just assign, so to say, by value. And now the ownership moved into the moved C. And note that we didn't write mute here, so we now own the caterpillar, but we cannot modify it. Okay. And what does the borrow checker in Rust ensure? Let's first see what there are problems with commonly used languages that have manual memory management. There are problems like used after free. So you free a piece of memory and you still have a reference to that, and you dereference that. That's called dangling pointer. Or you free a piece of memory twice, or you're not freeing memory at all. There can be memory leaks in managed languages as well, but I mean the classical not manually freeing a piece of memory. And which is not really memory management, but mostly memory access, is buffer over and underflows. All right, and these problems are common problems that lead to safety and security issues, like unstable programs or exploitable programs. So the borrow checker of Rust will prevent the first three problems. The last one is prevented by the array implementation. So if you index into an array, there will be bounce checks. But if you use the iterator API to iterate over elements in, for example, an array, then the compiler will optimize it in a way that it looks in the end, the assembly in the end looks like if you wrote like 4 loops yourself. So there will be no additional bounce checks. All right, just to the credit of C++ 11 and higher and the guidelines support library, they tackle many of the problems, and there are even further initiatives in the C++ community with flow analysis to get rid of most of the problems. But actually, the rules in the borrow checker are even stronger to prevent even more things. We will see later. So that even when C++ catches up with these security issues, there is value in the borrow checker. So let's see like a common C++ problem. We define a vector. A vector allocates a piece of memory on the heap. where it stores the given element 0. We then take a reference to the first element in this vector. We then iterate over the from 1 to 4 and add more elements, and at some point the buffer is full. And when we add another element, the vector will allocate a bigger piece of memory, copy all the elements over, and free the old piece of memory, the old buffer. So now we have a dangling pointer, because E points to a piece of memory that is now freed. What happens when we print this then? Who knows? If you go to this URL, which is using GCC, and you run it, it will print a random number. I want to point out, if you use a experimental version of the Clang C compiler with a special flag, which you can see here, the compiler will actually also complain in C++, all right? But this is stuff coming up in the future where there's flow analysis and dangling pointers can be detected. Okay, so what are the rules of the borrow checker that ensure this safe memory management? So every single piece of memory has an owner, and just one owner, a single owner at a time. When the owner goes out of scope, the memory is freed. References to owned memory, so borrowed or aliased pieces of memory, they must not outlive the owned memory that is referenced, all right? And this is done by tracking lifetimes. There are also explicit lifetimes. If the compiler is not sure about the lifetimes, you can annotate the lifetimes. I will not talk about that. See the additional material on explicit lifetimes if you're interested. And there is just single exclusive mutable access to a variable, okay? If you have a mutable access to a variable, there must not be an immutable other access. Or you can have multiple immutable access to a piece of memory, but then no mutable access at the same time. This is very strong. These are very strong rules, and therefore there are some types in the standard library that let you do this checks at runtime, not at compile time, so you have a little bit of freedom there, but these are types, and when you see the types, you know that there's runtime cost associated with it. For example, the reference counting is basically a shared ownership. Okay, and if these last two rules are somehow familiar to you, they somehow feel familiar, these prevent data races. So there is no data race in safe Rust, all right? So if you have, let's define a data race, it's if you have multiple concurrent access to variables, to a piece of memory, and at least one is mutable, you may have a data race, all right? So at compile time, Rust ensures that there are no data races. You can still have deadlocks, for example, if you use mutexes or something, but there are no data races, which enables something that the Rust community calls fearless concurrency. So you don't have to be like very pessimistic about with locks and synchronization, because you know there cannot be data races. Okay, so these harsh constraints enable you to do something. But these are also rules that a new Rust programmer often bangs their head against. It's called fighting the borrow checker, and everyone new to Rust will every now and then fight the borrow checker until like the mind goes click and they program in the way that follows the rules. Also, like these rules, if you in Java have seen the concurrent modification exception, this will not happen in Rust because of these rules. All right, this Rust example may look familiar to you if you remember the C++ example, because it does exactly the same. Note that we have in Rust also other container types like hash maps and sets and so on to manage memory on the heap. Also, there is a box type, which is something like a unique pointer. So you put an element on the heap and then own the reference to it. And in Rust, there's no classic for loop. So there's always this for in loop, which is very similar to Java's for in loop, and C++'s for in loop now. And what does the Rust compiler say? The compiler says, I cannot compile this because you have an immutable borrow at this line and a mutable borrow at the other line, and our rules prevent that. Okay, so you can't have this dangling pointer. Control flow, I won't talk much about control flow. There are if expressions, match expressions we've seen so far. Loops, the for loop we've seen, while loops is like while loops in every other language. Infinite loop is just the keyword loop and the block will be evaluated until eternity unless you break out of it. And the interesting thing about this loop is you can break with a value out of the loop. The question mark operator is not like the null save operator that you know from other languages like Kotlin and so on. It is a suffix that can be used on optionals and results and will extract the positive case, so either the sum or the OK, and will return from the function with either an empty option or an error. So it feels a bit like exceptions in other languages, just you see exactly when you unwrap an option or a result where an error may be propagated up the call chain. Okay, behavior for types. There is no classical, Rust is no classical object-oriented language. It's similar as in Go. You have no inheritance between data types, but you have these traits. Traits are like interfaces in Java, and you can basically inherit from them. It's not actually inheritance, but it's like inheritance. Let's take an example. We have the caterpillar again, and we have a butterfly, and now let's implement this butterfly. We have this impl block, and we define functions associated with the caterpillar. First, is like in Java, you would say a static factory functions, because there is no new keyword. These static functions called new are customary in Rust to create instances. Okay, so here we create the caterpillar, set hunger to a default value, which is very hungry, and assign the string, and return the caterpillar. Note that there is no return keyword and no semicolon. In Rust, when you return from an expression, when the last expression doesn't have a semicolon, it's implicitly returned. Right? So we don't have to write return, and when this value created here is returned, you don't write a semicolon. So now we have an eat method. This is a method. It takes a mutable self-reference. This is like a this pointer in Java or C++. It's very explicit here because this could be mutable or immutable, but we have a mutable. We use a mutable reference here because we want to modify the hunger field. All right, we reduce hunger by eating. And when transforming, we transform the caterpillar into a butterfly. And since this is taken by value, we take ownership of self and drop it in the end because we don't pass it on again. So in the end here, the caterpillar is gone and we have a butterfly. All right, so let's use it. We create a caterpillar. We call some method here, and note that we pass just a reference and not a mutable reference. So actually, the compiler would complain here because we cannot call eat on this parameter, because eat would need a mutable reference. This is different than in Java. If you have a final field in Java that reference, or a final variable that reference an object, you can still call functions on that object or methods on that object that modify the state. So here in Rust, it's immutability all the way down, all right? Okay, so then we call transform. We transform the caterpillar into a butterfly. The caterpillar is gone. If we now try to access caterpillar again, the compiler will complain again because there is no caterpillar anymore. It's just a butterfly. Okay. Traits, you can have interfaces. I will go faster through them because my time is limited here. So this is an interface. We can implement an interface for a data type and then later on use the methods that we defined on that interface. Okay, IDE story. So Rust has this thing called the Rust language server, which implements the Rust language server protocol. And this can be used in different IDEs to provide the smarts, so to say. It is still in preview status. It is sometimes a bit unstable, and completion results for code completion are not always this great. And the Rust compiler needs, at the moment, some refactoring to make this work properly. And I think this will be sometime next year where there are like reliable code completion results, for example. Okay, the Corrosion Rust IDE builds on the, or stands on the shoulders of giants. Okay. It uses CDT, the C development tools for the debugging story. It uses the Rust language server, which is then consumed via LSP4J and LSP4E to do like syntax, completions and type hierarchy and stuff like that. And it uses TME4E for syntax highlighting. All right, so what are a couple of current features, like compile error markers, also in the editor, but is now hidden by the code completion, syntax coloring, code completion, find references, an outline view, and even more things like new project wizard, quick outline, quick fixes, rename, refactoring, like the basic things that you would expect from an IDE, basically, right? But there are some limitations. So, but most of the limitations are because of the RLS being so limited, all right? So flat outline view, there's no tree view in the outline. There's no good unit test UI, and not that much refactoring, and a couple of other minor things, all right? So my experience with Corrosion and the RLS is, if you're used to Eclipse, then Corrosion makes you feel right at home, right? And this is the story of language server protocol. You can easily integrate these language servers into an IDE that you like, and can happily use the tool that you are used to. And the stability of RLS and Corrosion, the combo, it got much better over the year. In the beginning, it was not that great, and I think this was mostly RLS's fault, but even then, you sometimes saw like exceptions in the UI. I don't see any exceptions anymore in the UI. And every now and then, even now, the Rust language server stops working, and you have to have a hard restart of Eclipse. But it's not that common anymore. And sometimes when you want to report errors that pop up, you don't really know, like, where do I report it? Because it's like a huge stack that it goes through. But usually you would open an error on Corrosion, and the team will then open errors on the actual problematic part. So, conclusion, Rust is a friendly systems programming language. What do we mean? It comes already with a build tool and a package manager, and if you're coming from a C++ background, you know that you have a hard time there. And it has fewer sharp edges compared to C and C++. Okay, you will fight the borrow checker and the compiler in the beginning, but later on, it is you won't get that much errors at runtime. And it guides you to perform in code, so you can use types. Yeah, all right, I have to stop, so let's, okay, 1 minute. You can use types that have runtime overhead, but you really see it. And Rust and Eclipse have like really great communities. This is the Rust mascot, the Ferris. And thanks to everyone, because the Rust community is really great. And vote. And here are some learning materials. Whew. All right, since I had to stop, if you have